and he was talking about making the fullerenes larger. So, and they'd meet at some point because he was going to the moon. He wanted to have something big. That was the 1980s event that got me into something. And 1990, we had the idea, both of us had the idea, that this might have some connection with nanotubes. And so that's how I got into nanotubes. But Endo Sensei had worked in nanotubes in the 1970s for his thesis. So he was a good agent to help me with that. So our collaboration expanded at that point. I used to go to Japan every year, a few times, to work with him, and he came to the MIT a few times every year to work with me, so we became really good friends. So that was 1990. The Japanese government sponsored a fellowship for very young scientists just starting their career. And two of them decided that they'd like to spend some time in Cambridge, Massachusetts, and selected me as their sponsor. So I said, yes, that'd be very fine. So you can come. And they didn't know each other. And so one of them was Fujita, and the other one was Saito. And they met at MIT. They didn't know each other. They met at MIT. And they asked me what they should work on. So I thought that since they knew each other, that if they worked together, they would be much more effective in working because they would have some people that they could speak Japanese to and relax and all that stuff. So that's how they got to know each other, and they were thinking of a project to work on. So they came to me and asked me what to do. So I said, we had this conference with Smalley, and he suggested that we should take a nanotube and stretch it out to make a single wall carbon fiber. That's what we talked about at this conference. So I said, I have no idea to do it, but maybe before we start the experiment, we should have somebody calculate if it would be interesting and worthwhile to make a controlled carbon nanotube. I didn't know that you knew how to do all those kinds of things at the time, so maybe we would have come to you. But anyway, we went to Smalley. And he gave us some ideas, and that led to our doing metallic and semiconducting nanotubes. That's a very important topic. We have a lot about that in this conference. So that was my 1990 work, and then we published many papers on nanotubes, of course. 2000, so I went from 1D to 2D in 2000. And you were responsible for that. When these folks got the Nobel Prize, I knew about all these other things with graphene, and then we were always peeling it, so I was familiar with graphene. That was very familiar. So, but I was, by that time, I was in my 70s, and I wasn't really sure I wanted to get into this at that age, but I did anyway because you were so persuasive. You give a great talk. So I decided I'll go into graphene. And well, just around that time, I became head of the Office of Science from the US, and I got influential in the kind of research that we should be doing in this country. So I was proselytizing for trying to catch up with the Brits with no money because nobody gave any grants for that. So things were a little bit austere here, starting at that time. So 2010, I got into 3D, and again, and what I'm doing now, so looking to the future, what I'm planning to do is go back to everything, which is what I was doing in 1950. So my career in science has been like this. And I'll sit down now. Thank you.
Well, I do have some slides. Oh.
Whatever you'd like.
What's that?
There is fine.
Okay. All right. Excuse me. Well, okay, I'll also start with a little retrospective. I was working in surface science and molecular beam scattering in 1987, and I decided in 1988 and 89 that clusters sounded like an exciting field, and Rick Smalley was making a big splash with all kinds of metal clusters, and Cox and Calder at Exxon. And clusters just seemed like an exciting thing. So in 1989, I was making the case to our managers that we should get into this. And as a poster child for this, I took the fullerenes because it was an amazing story, and the only data that existed was derived from sort of molecular beams that were zipping through a vacuum chamber, and then they were gone, right? So I used the illustrations. Could we have the next slide, please? The illustrations from Harry Kroto's famous 1988 paper, Space, Stars, C60, and Soot, just as part of my pitch. So instead of having a molecular beam of these things, we actually wanted to make them and have them in your hand so you can get some real data. So we started simple, which means we just took the, whoops, back one, please. There we go. We took a laser and, thank you. Let's see, where's the button? Anyway. We vaporized graphite in a chamber with argon and just caught the debris on a copper bar. And that bar we put into a surface-sensitive mass spec, and when we desorbed the material from the surface and then ionized it and took a time-of-flight mass spectrum, we saw the famous fullerene spectrum. So at that point we had nanograms of material, and we could publish our first paper that said, okay, we've captured these things. Does that one work? I mean, this one probably works too. I just couldn't find the button. Okay, that's good. Yeah, thank you. So with nanograms, we could publish a paper that said they were there on a surface, and you'll see received August 7th. Turns out that was actually the day that Kretschmer and Huffman's paper on fullerenes was received at Nature. So it was a competitive time. Of course, they had a lot more stuff than we did.
Yeah.
Could I have the next one? Okay. At that point, somebody pointed out Kretschmer and Huffman's work on IR spectroscopy of a soot they'd made just by running a current through a little graphite bar. A setup I described as a pencil lead and a battery. So we read that paper, and we immediately got a 100 amp power supply and ran a current through a little graphite bar. And we had a glass plate on the top that we caught the smoke on and scraped it off with a razor blade. And what it turned out was you could take that scraped off soot and warm it up slightly, and C60 would be the very first and only thing to sublime out if you were gentle. If you warmed it up a little bit more, C60 and C70 would sublime out. So in that way, we could make samples that let us take the Raman spectrum of C60 and C70, and we could sublime some onto a surface and get an STM image of these balls all on a surface, arranged in a nice pattern. And finally, with 60 micrograms of material, my colleague Bob Johnson was able to get the famous one-line spectrum, NMR spectrum of C60. Of course, we were in a heated competition. We didn't quite know it at that point, but we were pretty sure we were in a competition with Harry Kroto. And when we got our spectrum, we sent him a copy of the paper, and he sent back a fax that said, congratulations on the one line. It is nice that C60 can make a lot of people happy. There's lots of it to go around. And then it turned out that his paper was received a week before ours, so he actually won that competition. All right. So now we're at micrograms. If we go one step further, one slide further. So now, one day I called up Rick Smalley, and he said, oh, yeah, we're using an arc. So we got in the car and drove down the street to Orchard Supply Hardware and bought an arc welder that looks very much like that one, and took it back to the lab, and pretty soon we were making grams of fullerenes. So now the gram scale, I call the research scale here, and with that we could do a lot of experiments that I don't have time to describe, but at about that same time we had a visit from Professor Kroto, and he gave a beautiful talk on his astrophysical work and on the fullerenes and all of this. And one slight, touching story was that after this talk, he was talking to Bob Johnson and I, and he said, going around 5 years giving these lectures and trying to teach the world about carbon, giving hundreds and hundreds of talks, he said sometimes he felt like a puppet who would be taken out of the case, and he'd go up and perform on the stage, and then you'd put him back in the case and carry him off to the next engagement. But it was a lot of work to sort of try to teach the world about this, the carbon and C60, but he did a great job of it, and I'm very grateful to him and Robert Curl and Rick Smalley providing the sort of inspiration and sort of helping us get started in fullerenes. Okay, so if we go to the next slide, once we had this arc generator, we did one more trick that was very useful. We drilled out the center of the carbon rod and put metals in the middle of the rod and vaporized the carbon and the metals at the same time. That was partly inspired by the Rice group as well, who said that they could put lanthanum, for example, in a carbon cage. So in that way, we eventually found this molecule here, which had 3 scandiums in a carbon cage, and gave this remarkable EPR spectrum. And it led to the question, could we make carbon-encapsulated ferromagnets? So it was that effort to just try to see if we could make a carbon-encapsulated ferromagnet that led us to put cobalt in a carbon rod and vaporize that. And then, exactly as we expected, we got single-wall nanotubes. Well, actually, we had no idea we'd get single-wall nanotubes. But when we looked, what we saw was these spiderweb things in the chamber, and Robbie Byers downstairs did the TEM work to show that indeed we had single-wall nanotubes, which I have to say led to my first and only other opportunity to go to a Carbon Society meeting in 2004, which was very, very nice, maybe one of the nicest meetings I've been to.
Thank you.
But State College is very nice too, and the organizers had a great time.
Lovely. We have a healthy competition too.
Yeah,
Lovely.
okay. So this is still now what I'd call research scale nanocarbon. If you go to the next slide. This, I'm not sure I entirely believe, but if I play with Google Scholar for a while, these are the curves I get for searches on papers per year: carbon in nanotube, single in nanotube, graphene, and fullerene. So if you just take the top 2 and fullerene, no, sorry, leave out single in nanotube, take the 3, carbon, graphene, and fullerene, then we end up with these curves, which are kind of interesting. It says that maybe nanotube work is turning over a little bit. Graphene is still heading up, and congratulations. But one interesting thing, the part that I don't really believe, is you just sum all these up cumulatively, you come up with 1 million articles on nanocarbon, which it could be true. It's just difficult to get your mind around. And if you say that research scale means that you have about 1 gram of material you're going to do your experiments with, then what we say is that for 1 million articles, it takes about a metric ton of nanocarbon. All right, so that's research scale. So if we go to the next slide. I won't describe this in detail because it would take too long, but one of the things IBM Research has been working on now for 20 years, started by Feather Navuris and continuing now under Shujen Han, is trying to make digital logic circuits with carbon nanotubes. And they recently published a nice review article that had two pieces. It was a review, it was a modeling of how you could improve the performance of a microprocessor using carbon nanotubes. And their estimate was you could maybe get 5 times more performance at a given power level. And the power level set by at the point at which things start to melt these days. So it's quite important to stay below that level. And the other thing they did was they reviewed all of the progress that's been made that I can't summarize, but the keys to being able to do this are well known. You have to select all semiconducting tubes, preferably all about 1.7 nanometers in diameter. You have to place them precisely in arrays in the right place on your chip, and then you have to contact them well. So this paper is a very nice summary of how people have used density gradient, centrifugation, column chromatography, polymer extraction, and so forth to try to make pure semiconducting tubes. And I know there have been some very nice papers here that reported new progress in this direction. And then they also review the placement question. Anyway, so if we go to the next one, there's a separate sort of fallback position. They have if they can't separate them and they can't place them exactly right, well, they can make a cryptographic key chip by seeding carbon nanotubes into an array of cross points there, and then it's okay to have random metallic here, semiconducting here, none there, and so forth, because it generates what they call a non-clonable chip that basically you can't copy, but it will uniquely identify you as the possessor of that chip. All right, so next. So what is the real scale of carbon materials if we want to talk about carbon materials in general? We've said that a metric ton does the research, but the world scale for carbon is 10 orders of magnitude more than that. I mean, the amount of oil and coal produced, for example, is on the order of 10 gigatons a year. Now, 10 to the 10 is an interesting number because it's also the number of people that we're tending toward in the world. So, one slightly backwards answer to the future of carbon materials is that they have to be used much less than they are now. But the corollary is you have to use them more intelligently. And that's, obviously the goal of people in this field. I mean, to use carbon well, but less of it. So if we go to the next slide, then, this is kind of a more generic slide that you're all very familiar with. I mean, I don't have to tell you that carbon materials can add strength, conductivity, and so forth, all these good things. And we've already heard, yesterday from Jeff Don, how much carbon is going into batteries for storage. And various people have noted that you can make automobiles lighter and more efficient by making carbon fiber parts instead of steel parts. So, if there's various people trying to push the scale of carbon fiber that's being used. I mentioned Oak Ridge and BMW, but there's many others, of course. So, if the result of a smart world is that we all drive solar-powered Teslas, it might not be so terrible, right? Okay, so the last one is due to Oxio, who I know have representatives here. I found this curious thing on the web, the Manifesto of the Carbon Century. Their basic message is do more with less by adding nanotubes to everything, basically. And they make a nice claim that this will change basically the world and civilization can overcome its challenges using carbon. We have to hope that they're right, of course. But the last thing that's slightly amusing is I looked up their patent and I compared their diagram for a carbon nanotube generator to our diagram in our patent back in '95. And they look fairly similar to me, with one key difference, that theirs produces nanotubes at a rate about 1 million times faster than ours. So, progress, I guess. Anyway, thank you, that's all I have. Rose.
Mine. Okay. First of all, I'd like to show my hearty thanks to invite me this fascinating opportunity. My talk is on this slide. And first plenary talk by the Professor Ferrari, he showed the graphite pencil, which is developed at 1565. The new type of carbon, appearance of new type of carbon, is every time a historical viewpoint create new civilization. So the carbon is a very important trigger to new civilization. So pencil is one example for history. And because of the England and France, a long time of the war, the England stopped the export of pencil, which is produced at Bordeaux. And Napoleon started to develop the pencil, which is made by the sintering of graphite powder and some clays. That is just present years of the pencil. And the second one, pencil is a little may know, the size is 0.3 millimeter. And the second innovative carbon appearance was the lighting bulb made by the carbon. The Japanese Kyoto bamboo was used by Edison to make the carbon filament. And this was very much changed the people's life by this lighting bulb. And a lot of the people visited to Edison laboratory located at Melon Park, which is shown in the Edison book. And even the special train was prepared to the station. A lot of people still can't use the train. So the so big innovation at that age. And carbon filament was about 100 micron in size, diameter. And next one is the carbon fiber. The size is 10 times smaller than carbon filament. This is around 10 micrometer in diameter, which is developed at around 1960 or early 1970. And this is very important to open the aerospace era. And this could be very, very important for human being history. Our ancestor, long time ago, moved from in the water to land. And this space for human being go to space against the Earth's gravity should be second big event in our human history. It's realized by the lightweight and strongest material made by carbon fiber. The diameter is 10 micron. And the next one is the carbon-based anode lithium-ion battery. This opened the mobile electronics era. And you may see this one. As a function of the year, this is the energy density per weight, and this is energy density per size. Okay, so year by year, the energy density improved a lot. During the 20 years, the first one developed by Sony. Past 20 years, the volume become 2 to 3 times higher energy density. For the lead acid battery, which was developed at 1860, since 150 years, long time, the performance only improved 50%. For lithium-ion battery-based carbon become 300% bigger energy density. That's mainly contributed by the anode carbon technology. Carbon is so important. And now, for the lithium-ion battery, it's based on the graphite intercalation compound. Professor Dresselhaus showed on that. The size of this material is focused to the several nanometer or less. So the size of the material, which is focused to the carbon, is year by year becoming small and small. And by the intercalation compound, it's become the order the nanometer or less. And C60 carbon nanotube and graphene is just nanocarbon, which has the nanometer size in dimension, and that is a very important key to determine the performance of the materials. And United States, the most important nanotechnology project has been done in the United States called as NNI. The NNI started in 2000, and Professor Dresselhaus related a lot to this program. And they said, facilitate transfer of new technology into products for economic growth, job, and other public benefit. This is the goal. So not only scientific development, but also the technological development is so important to contribute to society. And still now, after 12 years passed on the NNI, they say, here you can see, a small working together toward a shared vision of a future in which the ability to understand and control matter at the nanoscale lead to evolution in technology and industry that benefit society. So the controllability of the nano-sized dimension and structural analysis is so important in this material. And for that case, the Rosalind Franklin, this also many people used and showed on her. She developed very important carbon model here. Still, we use, a lot of people are very familiar for Franklin model, okay? She found this structural model from the X-ray diffraction pattern. He has a very strong ability to see the real space image from reciprocal image of X-ray diffraction. He published her paper 1951, and about 2 years later, he found double helix X-ray diffraction. That is very important. So she is a carbon scientist, and she has a lot of experiment on carbon, and she established very important Franklin model. That background can help her to understand the double helix image of DNA. So now, for us, the nanocarbon is an era to innovate to society. And at that case, as I show you, the controllability of nanoscale structure is so important. Not accidental product. Controllability is very, very important. For our case, This is collaborated with Professor Dresselhaus. By doping to graphite, you can see here, this is the boron. And if we can dope the boron to important atomic scale precision, that could be very, very promising in future. Or some periodic doping to graphite. That could be also should be interesting by the Professor Guy. And for carbon nanotube, still a lot of issues should be resolved. How such a small iron particle can grow the tube so fast, and what mechanism? Many papers has been published, but still a lot of things should be cleared. You can see the carbon layer go out from such a small catalytic particle. And the speed is very, very fast. So by combining such kind of the supercomputational chemistry, next phase should be more precisely control the chirality of carbon nanotube to get the targeted performance by controlling the nanoscale structure. That could be very important. This work has been collaborated with Professor Kroto. If we can control the nanosized structure of carbon nanotube made by single wall or double wall or triple wall, we can get very lightweight and high current density possible for transmission, power transmission conductive wire in future. And from the viewpoint of history, new carbon every time appeared by new process to form carbon. So sometimes CVD catalytic process or the plasma decomposition of polymer. So from sp2, sp3, and sp, and sometimes perhaps the liquid graphite. This also I little bit worked with Professor Dresselhaus a long time ago. If we can get liquid carbon, and if we can spin the liquid carbon directly, that could be one of the best carbon fibers, which could have the most strongest in the world, the fibrous material of carbon. And 21st century is a very important era for the environment, not